In an OpenCL environment, there are different types of memory. In an OpenCL environment, there are different types of memory components. On the device side, when we execute a kernel function, this kernel function can be executed by multiple work groups, can be executed by multiple work items organized in groups. We call it work groups. Within each work item, it can have its own private memory space, and this private memory is not accessible to other work items, even in the same work group. Within a work group, there is a local memory which can be shared by multiple work items. And keep in mind, this local memory and private memory are oftentimes on-chip memory components. Oftentimes on-chip components. On the device side, off the chip, there's a global memory which is shared by all the work items in all the work groups. Within the global memory, there's a small memory space called a constant memory that is used to store constants. On the host side, we saw the familiar host memory, which is used by the host CPU during computation. And the host and device use certain interconnects such as PCIe, QPI, or AXI to communicate, to exchange data. When we have a kernel function, our goal is to compile the kernel function into binary to be executed on the accelerator. The accelerators can be FPGAs, GPUs, etc. For example, when we have a kernel function sum like this, and within each kernel function, we're performing element-wise addition. So what we do is we load the data from these two vectors and using the ID XID. So we'll have a load and load to read two operands from the memory, and then we perform the addition. The sum of these two numbers will be stored into the destination memory object. So in this kernel function, we have load and load, add and store. And our goal is to execute multiple of these kernel functions. So when we map this kernel function into FPGA, we will see that for each of these kernel, we have resources allocated to perform load, to read operands from memory, and then we have an adder to perform the addition operation. The result will be stored into memory using this store unit. And because we have a large amount of resources available on FPGA, so to replicate this or to instantiate multiple kernels, we'll use multiple of these resources to build such structures. Also on the FPGA chip, we have other resources allocated for communication, for example, to talk to a PCIe bus or to communicate with off-chip memory components. OpenCL applications for FPGA, we start with a kernel function in the kernel source code. And then we use OpenCL compiler to generate high-level description language. This could be VHDL or Verilog. Then this high-level description language implementation will be compiled by a typical HDL development environment such as Quartus to generate FPGA programming bitstream. And in this process, the description of the FPGA board will be used by the Quartus development tool for this bitstream generation, specifically for mapping and routing. On the host side, we also have a host program, and this host program will be compiled with a typical C or C++ compiler and linked with OpenCL runtime library and to generate the binary executable. In this process, the OpenCL SDK comes with the host side runtime environment. Once we build the binary for the FPGA and also for the host side application, we can use OpenCL runtime environment to execute this binary. On the host side, This runtime environment comes with OS driver, low-level description of the hardware, and also OpenCL API implementation library. And this host-side application will be executed on the processor. The compiler on the device side, for the case of Intel FPGA, will have a Intel FPGA offline compiler called AOC, which will produce the complete FPGA design, which includes the accelerators, that is the kernel functions, also the data path, and also all the memory structures used by the kernels. So everything that we describe or used in the kernel function will be compiled and generated by the offline compiler to map those resources on the FPGA. The board support packages come with the SDK environment, supports the PCIe communication, and also the memory controllers that are useful for talking to off-chip components. So altogether, the runtime environment on the host side and also the board support packages on the device will be able to allow the kernel functions to be executed and be able to communicate with the other resources on the host side and also on the other memory components.